A huge problem of the previous dynamic programming algorithm is the memory requirement. When we have to align a 1000 character string to another 1000 character string, we need to store a million variables plus a million backtracking points. How can we avoid it? If we were able to store only the middle point, our life will be easier. How do we do it? Imagine that we are able to know that this point, the violet one, is the one in the middle. What do I mean in the middle? In the middle column. Here we have 7 columns, and the third one is the middle one. In this case, I know that in the third column, the column number 4, my apology, the third node from the bottom is the one that is the middle node, where an optimal alignment path crosses the middle column. And I'm going to apply a divide and conquer approach. Because this is a middle point, I know that I can exclude this part. And because this is again a middle point, and because I'm going only south and west, I can exclude this part. So I'm going to get half of the nodes of what I have before. The problem is how to find this middle node in linear space. Okay, we speak about memory here. In linear space, finding the longest path in the alignment graph requires storing all backtracking pointers, so it is not linear, it's quadratic as a space. And so is O of nm, while the length of the longest path in the alignment graph does not require storing any backtracking pointer. How do I calculate the length? Using only a reduced amount of memory. I'm going to store only the leftmost column. I start in this way. Now, to calculate this column, I need only the leftmost one, this one. The same thing, to calculate this column, I need only the leftmost one. I'm not going to store any of this data. So in reality, I'm going to use 1, 2, 3, 4, 5, 6 variables to calculate the alignment graph. I'm not going to have the alignment graph, I'm going to have only the total length. And I know that the total length is 4. And this is the optimal length. What I wish to stress is that if I'm going to get this point here, and I'm going to reverse the direction of the row, I mean, I'm going from this node to this node, from this node to this node, from this node to this node. And I'm going to sum the weight of the arcs, I'm going to obtain this number anyway, 4, that will be the maximum of this column. So, can we find the middle node without constructing the longest path? So we call I path a longest path among paths that visit each node in the middle column. So I have a column, the middle column, and I call path 1, path 2, path 3, path 4, path 5. I path. 4 paths that visit the node in the middle column. Why 4? 1, 2, 3, 4. And the length of 5 is the length of an I path. The length of 0 is 2. We come back to the previous slide. Yes. The length from 0 is 2. The length of this point from 0 is 2. And the length of this point from here is again 2. And the total sum is 4, that in this case I should put here. So I know that the length of the not known path that converge here is 4. I'm going to calculate the same length for all nodes, and then notice that this is the longest one. As a consequence, I'm going to select this one as the middle node. So the length of the each node is the sum of the weight from source to I to the sum from the weight from I to sink. So now I can recursively apply this algorithm. From source I have this point, and to sink I have this point. And how much time did it take to find the middle node? Here, I'm not speaking about memory, I'm speaking about time. I have a trade-off memory time. I have, in this case, to identify the middle node, to investigate half of the node from source and half of the node from sink. So the entire area. So I didn't find in reality a good algorithm, because to find one node, I have anyway a quadratic time. But once I have it, all the further problems are divided by 2. Why? Because I know that I can arrive from this node only from the left or from the top. And I can arrive to this node only from the right or from the bottom. So each subproblem can be conquered in half of the time of its area. So I have a linear game. But when I'm going to apply the system recursively, this f become 1 divided by 2 power n. And so it will be much more quicker methodology. I will need less memory to do it. So again, we do not find in this situation a good algorithm. For the problems, again, as we can see, we have an increasing in the computational time to decrease our memory footprint. And the computational time is going to be limited by 2. This is a standard succession problem. So now we speak about the middle edge. The middle edge is the edge starting in an optimal path at the middle node. So before we have the middle node problem, now we have the middle edge problem. The middle edge in linear space. Find a middle edge in the alignment graph in linear space. The input is 2 strings and a matrix score, and the output is a middle edge in the alignment graph of these strings. So this is the middle edge. It would be only this one, diagonal, or south, or on the right. This is a recursive linear space alignment. I'm inviting you to review this algorithm later. And now this video is concluded. See you the next time.